Last topic of the unit now. Building upon the whole two-dimensional vector analysis that we've done, today we're going to talk about projectile motion. Let me define a projectile first. A projectile that is an object that moves through the air under the influence of just gravity, just like that bus did in the video that we just showed you from Speed. The bus, when it left one side of the washed-out bridge, goes to the other side. It's a projectile because at that point, it's under the influence of just gravity. Now, if you've taken Math 20, you're probably going to recognize this term, at least I hope you'll recognize this term. When a projectile moves through the air under the influence of just gravity, the shape of the path should always be a parabola, like this, right? You guys have seen this shape before, except it's an upside-down parabola, because it's going to look more like this. Even when an object leaves the edge of a building, maybe a ball is kicked off the edge of a building, like this, that's still a half of a parabola. So it's not going to do the whole Wile E. Coyote thing, go off the edge, look down, and then fall straight down. Okay, it's not going to go down like this in a straight line. It's going to always follow a parabolic path. Now, sometimes that parabola might be stretched out. Sometimes it might be narrower and higher, depending upon the initial velocity and so on of the object, but it's always going to be a parabola. Yep. That's a good question. No, that's a good question. That would be the exception to that. If it drops straight down, we wouldn't call that a parabola, right? But you're going to see the equation that we would describe it with reminds us a lot of a parabola still. We'll talk about that in a few moments. Now, because there's only one force acting on a parabola, and that's going to be gravity, and gravity acts downwards, the horizontal velocity, and again, we know that we have two components here. There's an x velocity and there's a y velocity. The horizontal velocity, the x velocity, is constant. It's not speeding up or slowing down. Gravity acts down. A downward gravity isn't going to cause us to speed up or slow down horizontally. Therefore, the x component is always constant velocity. And because of that, there's only one equation that's valid for the x component. It's our group A equation. We're going to end up breaking these problems down into two components, x and y, kind of like we did for those navigation problems, kind of like we did for those vector addition problems that we've done over the last couple of weeks. But this time when we break it into x's and y's, we're going to write down equations for x and y. And for x, it's going to be v is equal to delta d over delta t. Now, for the y component, we know that gravity acts. So it's going to be acceleration. That means that's a group B problem. The x component is group A, the y component is group B. We're allowed to use any of those acceleration equations for the y component. There's one that I'm almost always going to try first, but we're allowed to try all of them. The f squared is equal to vi squared plus 2ad. There we go. They're all valid. But we know for sure for the x component, I've got to use this one. For the y component, even though they're all valid, it's most likely that I'm going to use that one. V is equal to vit plus 1 FET squared. So when you're dealing with these problems, always break it into two components, x and y. Always start with v equals d over t for the x component, and probably start with d is equal to vit plus 1 FET squared for the y component. Listen, if it doesn't work for you, okay, if that d is equal to vit plus 1 FET squared doesn't work for you, then you have other options. You have 4 other options for your group B equations. But try that one first, because it does work 95% of the time. You might as well go with the one that works the most often. And if it doesn't work, you'll figure that out. and you'll know to try something else. Best way to learn this stuff is to do it. So let's try a problem here. 2.10 on 107 says, head smashed in Buffalo. Notice we're in chapter 2 here now, guys. So if you haven't got chapter 2 downloaded, you should do that. We've been in chapter 2 for a little while. We just haven't needed our textbook because the problems that we've been doing have been on worksheets, right? Now we're going to go back to some problems in our textbook. So get chapter 2 if you don't have it already. Page 107, it says, head smashed in Buffalo jump near Fort McLeod, Alberta is a UNESCO World Heritage Site. Over 6,000 years ago, the Blackfoot people of the plains hunted North American bison by gathering herds and directing them over cliffs 20 meters tall. This is true. Okay, this is what they actually did. How many people have ever been to Head Smashed in Buffalo Jump? It's kind of neat there, right? The idea is literally, like, it's the simplest, most brilliant idea ever. You want buffalo meat? Like, don't go hunting buffalo. Buffalo aren't the smartest animals in the world. Okay, if you direct them in a certain direction, they'll run that way. So you kind of chase them in a certain direction. You kind of direct them in a certain direction towards the edge of the cliff. And then what do when they get to the edge of the cliff? Well, you and I would stop when we get to the edge of the cliff. Right, Peyton? We would stop. But buffalo don't. They just run right off the edge. What do? Well, they fall 20 meters and they die when they reach the bottom. So they cut them up, cut the meat off, cut the, whatever they do with them. I got all these bison that that they've just hunted, but without having to throw an arrow or put themselves in danger's way. So they go off this cliff that's like 20 meters high here. Let's draw a bison here. Yeah? He's all happy because he doesn't know what's coming. Being chased off the edge of the cliff. Hey, we know that when he goes off the edge of the cliff like this, he's not going to go like this. We know that he's not going to do the whole Wile E. Coyote thing and do this. Look down, oops, fall straight down. We know that he's going to follow what path? What's the shape of the path? It's going to be a parabola. At least it's going to be half a parabola, right? We know the cliff is 20 meters tall, by the way. So let's label that. It says, assuming the plane was flat, so the bison ran horizontally off the cliff there. In other words, not on a ramp. Although that would be much cooler if the bison ran off the ramp and went up like this instead of just like this. They run straight off at 18 meters per second. So let's label that speed there. These guys are running at 18 meters per second. That's pretty fast. We want to know how far from the base of the cliff the bison landed. In other words, we want to know this distance right there. Your strategy for solving this problem starts off as a bit of a recipe, but it ends off as do whatever you want, do whatever works. We're going to start off our recipe with writing down x and y for our x and y components. We're going to continue on with our recipe by writing down v is equal to d over t for x and d is equal to vit plus 1/2 at squared for y. Constant velocity for the x component. No gravity is acting horizontally, so it's a group A problem. Gravity is acting vertically, so the y component is a group B problem. We've got to use one of the group B equations. This is the one that works most often, so let's try that one first. Now's when the recipe kind of ends. Now it's kind of the free-for-all. Okay, now it's time to kind of freelance here. What do we do next? Plug numbers in. Plug numbers in where? Well, wherever you can. What are you solving for? Whatever you can solve for. Just get whatever. Plug whatever numbers you can plug in. Get whatever you can get. A lot of times when you do that, you're not going to get what you're looking for first. But that's okay. Because usually what happens is what you actually end up solving for first will help you to get whatever you want to get. So let's do that now. Do we know what the x component of the velocity is? Do we know how much of that velocity is? Remember, this is x, this is y. Do we know how much of that 18 meters per second is x component? Yeah, we do. What is it, Joseph? All of it. Plug it in, 18 meters per second. Don't worry about rearranging this equation right now. Okay, right now, just plug numbers in. Do we know what the horizontal displacement is? We don't, do we? This would be the horizontal displacement. That's what we're trying to find. Nor do we know how long it's in the air for. So what we just did isn't very helpful, but that's okay. It'll become helpful, at least most likely, in a few minutes. Okay, we have one equation and we have two unknowns. That's not very useful. Let's go to our other equation. Delta D for the y component. Do we know what that is? Do we know what the displacement for this bison is from start to finish vertically? Very, very close. What is it? Negative 20. Because it ends up 20 meters below where it started. Negative 20 meters. Do we know what VI is for the y component? How much of that 18 meters per second is y component? 0. Good. None of it is. So let's just cross that off. 0 times whatever the time is 0. A is neg 9.81 vertically. Okay, horizontally it's not, but vertically it is. T squared. Let's solve for T. It's not what we're looking for, but remember the strategy here is just do whatever you can do. Plug your numbers in, solve for something. Half of neg 9.81 is neg 4.905. Let's take the neg 4.905 over to the other side by dividing. And then what do we do to get T? Square root that, right? Let's do that on our calculator together here just to make sure that we can all get the same answer. We're going to say neg 20. Let's turn it on first. Let's say neg 20 divided by neg 4.905. Let's square root that. 2.0193. We're not done, but we're close. What are you going to do with that time? Yep, Jeremy? Yeah, we're going to take that time and put it back into here. How can we do that? Okay, the horizontal velocity was clearly different than the vertical velocity, 18 versus 0. The horizontal displacement was clearly different than the vertical displacement. The unknown horizontal velocity, the negative 20 vertical displacement. Okay, clearly different numbers. How can we put the time in x and y? Time doesn't have a direction. It's good for x and y because it's a scalar. So let's put that in. We get 18 equals delta D over 2.0193. And we're going to take that up by multiplying. We're going to solve for delta D, x component, which is really what we're looking for here, right? Take that number, multiply it by 18. We get 36.34 or 36.3 meters. So when this bison runs off the edge of the cliff, we know exactly where it's going to land, assuming that it's moving at that speed. We know it's going to land 36.3 meters away from the edge of the cliff. So you're the guy who's in charge of being down at the bottom of the cliff. You're standing at 30 meters from the edge of the cliff, base of the cliff. You can look up and see these bison flying over top of you without fear. There might be some fear, yes. There might be some fear. You can stand 37 meters away and, hey, it's fun. Hey, look at these bison falling down in front of me. Don't stand 36.3 meters, though, because that's where they're all going to land, if they're moving at that speed. I want you to take a look at these three questions for the next couple minutes of class and for homework this weekend, please. Remember, as you're doing these three questions, they're all new to you. You've never done this before. You're doing a new topic now, a new concept. Keep the example beside you as you're doing it. Don't forget that. Okay, it's okay. In fact, you should go back and look at the example that I just showed you. Okay? Don't try to remember it when you're working on this Sunday afternoon or Sunday evening, because you won't. Go back and try to understand it. All right? 3 questions. Homework for Monday. We'll check them over then. Okay, have a good weekend, everyone.